Greetings! So today I'm doing a short lesson on vector addition. In short, that's basically about trying to find something called the resultant. A resultant vector, by definition, is a single vector that replaces the other two. So if I have a vector A and another vector B, the resultant is simply one vector that replaces both of them. So instead of going up and right, I could just go up, right. And that there is my resultant. The problem I'm looking at, rather simple one. So I've got three vectors, F1, which is 100 newtons, another vector F2, that is 193,2 newtons, and another vector going down, F3, which I only know has a weight of 27.88 kg, which is going to be a force. Now the direction of these forces, this first vector here is taken 30 degrees from the vertical. That's what this dotted line represents. The other vector is 75 degrees from the horizontal, and I need to find the resultant of all three. So the first method I'm going to use for this is by scale diagram, and in particular looking at the palm method, short for parallelogram. So in setting up a scale, the first thing you need to do is pick out a scale that will fit these vectors. So 100 newtons, if I had to pick a scale for it, if I took 100 newtons to be 1 newton per centimeter, my diagram is going to be 100 centimeters, which is huge. So if I try something like 20 newtons per centimeter, then this vector would draw out as 5 centimeters, which is pretty reasonable. Okay, so I'm going to start by putting a dot here. That will be my reference point. This horizontal line here is my horizontal reference line. Let's call that X. And my vertical reference line here I call Y. You might also notice I'm using graph paper for this. It's actually incredibly useful if you're trying to not just measure things accurately, but also to draw your vertical and horizontal reference lines. Okay, so now my first vector, I'm going to need to measure the angle. So you need some technical equipment called a protractor. Putting the center dot on my reference point, lining up the 0 degrees with the vertical, I'm measuring 30 degrees from that line. So it would be on the inside of the protractor. 30 degrees is there. Next, to measure out this vector, 5 centimeters from the center point would roughly be here, but roughly isn't good enough on a scale diagram. To use a ruler very accurately, you actually need to turn it perpendicular to the page and look at it directly from the top to get as accurate a line as possible. So 5 centimeters there. There actually. Right, once you've drawn that line, put the vector head, that's the arrow on top of the vector, and indicate the angle. Its label, F1, is given in newtons, not centimeters. Right, then my second vector, F2, was 193. How you convert that into a scale? It's 193 newtons divided by 20 newtons for 1 centimeter. So that comes out to be 9.66 centimeters. The angle this time is 75 degrees from the horizontal. So lined up such that the vertical is on the 90 degrees, 0 is on the horizontal, and you're looking for 75 degrees from the x-axis, which is here. Again, check directly from the top, that is the angle. If you're even so much as 1 degree out, the entire accuracy of your scale diagram goes out even further. Okay, measuring this out as 9.66. Looking directly from the top, 9.66 centimeters is almost exactly at 9,7. Put in your vector head. And those are my two vectors drawn what we call tail to tail, which is the palm method. Now, constructing this palm requires using a set square and a ruler to draw parallel lines. Because after all, a parallelogram is just a quad with parallel lines. So how you do this is by setting your set square along one of the vectors, any one, and placing your ruler along the base, so that if you slide your set square along the ruler, kind of a tricky business, slide your set square along the ruler, you will always get a parallel line. So I'm sliding my set square up to the tip of the other vector and constructing a very light parallel guideline. It's very important that this line is actually parallel, which it is. Then you do the same with the other vector. So it takes a bit of practice, hand logic, trying to get these things, to work together. But like I did the first vector, put the set square along the bottom vector, the other side against your ruler, sliding it up and down so that you construct a parallel line. And you should construct it in such a way that your parallel line and your other guideline will meet up at a point. In this case, you see they actually don't, so all we do is extend it. The other problem you might notice is that, you see my diagram is kind of crossing over itself. That's not really so bad, just shows a kind of not considering how big this would be, but no matter, this is all in pencil. Okay, once you've constructed a parallelogram, the resultant in a parallelogram goes from the starting point to the opposite end of the parallelogram. There's no such thing as joining head to head. That's not the resultant, otherwise what is the point of drawing the parallelogram? Okay, so my resultant goes from the starting point all the way to the opposite end of the palm. Just to show it's the resultant, I'm using another color, our favorite color, red, just so it looks different to the other two vectors. Again, it is a vector, so it needs that vector head, and I'm going to label this as R. This vector here was F2, 193.2 newtons, and it was 75 degrees from the horizontal. Once you've constructed your resultant, you now have to calculate exactly what its magnitude is. To do this, we just have to measure the line in centimeters, and I get 13,5-ish. Again, hold your ruler perpendicular to get as accurate a value as you possibly can, because now I get 13,4 centimeters. To convert the 13,4 centimeters into newtons, all you do is you multiply it by the scale, and this gives me 268 newtons. So the resultant is 268 newtons. That is its magnitude. I next need to work out and check its direction. So to get this direction, I'm going to measure the angle from the vertical to the vector. So lining up my origin on that point, 0 at my vertical line, the reference line I do at the start, and this red line is exactly 1 degree to the right of the vertical. So how I can write this is as 1 degree, instead of saying right, I guess I could say clockwise, of the vertical. And this is the answer I get using a construction method, a scale diagram. So it's not going to be 100% perfect. For instance, if this was just so much as a millimeter out, that was a millimeter out, that was 1 degree out, all those errors add together and you might get a slightly different answer. So there's a certain amount of leniency regarding to this. So I would accept 267, 265 maybe, and between say 0 to 2 degrees. But that's the accuracy you get in a parallelogram method, especially one as crudely as I've done, which has taken me 10 minutes. Alright, looking at the other method of doing this, called the triangle method, or its other name is head to tail. So this is a bit more difficult to use when the vectors are starting at the same point, because to construct them from head to tail, I first need to draw this vector, and then from its head, draw the other vector. So the scale I'm going to use is exactly the same. So my starting points are exactly as they once were. Horizontal reference line, origin point. I need a 5 centimeter line going 30 degrees from the vertical. Vertical, 30 degrees, 5 centimeters. So, not cheating here, just putting my ruler at 6 centimeters over here and actually just going all the way up to 1. Slightly easier thing than trying to get your ruler exactly on 0. Make sure you look at it directly from the top. You can't see me doing that, promise I am. Vector head, that's F1, 100 newtons, 30 degrees that way. Now, from this point, we draw the second vector. So from this point, I again need another reference line, a vertical and a horizontal, so that I can put the angle in the right place. The angle I'm looking at, if you're looking at F2, is 75 degrees anti-clockwise from the horizontal. So from here, here's the horizontal, 75 degrees clockwise, line this up straight, make sure the horizontal is on 0, the vertical is on 90, 75 degrees clockwise will be here. The other way you could have actually looked at it is looking at this vector. Since you know that angles in a corner add up to 90 degrees, complementary angles, if this is 75, this would be 90 minus 75, which is 15. And then in the same way, you could have actually measured 15 degrees from the vertical to get to the same point. So let me draw that in. Just find a good number again. I think it was 9,66. But let's not assume things. It was 9,66. Make sure everything is perfectly lined up. 9,66, 7-ish almost. Goes up to here. Put a vector head. And then labels. So this was F2, 193,2 newtons, and I've taken it as 75 degrees anti-clockwise from the horizontal. So notice that. I could describe this vector as 75 degrees anti-clockwise from the horizontal. I think I said something different. 75 degrees anti-clockwise from the horizontal, or 15 degrees clockwise from the vertical. From the vertical, 15 degrees clockwise is the same as 75 degrees anti-clockwise from the horizontal. So either way you do it is fine, as long as you've connected the head to the tail. Right, so then my resultant for a triangle method goes from start to finish. So from my starting point to my ending point, red line. I'm not just joining these dots, they actually do line up to be perfectly vertical. Labeling that as R. And now the measurements. If I measure the length of this line, I get 13,7 centimeters. Let's quickly convert that. So it's 13,7 times 20 gives me 274 newtons. And the angle this time is 0 from the vertical. So the direction of this is vertical. So notice the two answers in the two ways I've done this. In the parallelogram method and the triangle method, the way they've drawn are almost exactly the same. There's a 1 degree of error, I would say, in the parallelogram method, but compare how extreme that is to the values that I get for the resultant. 268 to 274. So if you think about why that error is there, it's 6 newtons, and since my scale was 20, that is because I'm 0.3 millimeters out in my diagram. Anyway, once you've got the resultant of those two vectors, to find the resultant of the third vector, you are just using head to tail. Now there's no need for a scale diagram here if the vectors are in one direction. So if I take my resultant R as being 274 newtons up, or vertical, and the other vector F3, which was 27.88 kilograms. Now to change that force, or to change that mass rather, into a force, weight is mass times gravity. That's 27.88 times 9.8, which gives us 273.224 newtons. That is the force. So if I take these two vectors and I add them head to tail, I would be drawing this vector first, that's 274 up. From its head, the tail of the other vector, which is 273.224 newtons. And the resultant would go from the start to the finish, which is this miniaturized vector over here. In one dimension, you can just do a calculation for this, which would be 274 plus negative 273.224. So instead of just minusing them, why I've written it like this is to show that I have taken upward vectors as positive, and therefore downward vectors would be substituted as a negative value. Putting these numbers in, 274 minus 273.224, resultant I get is positive 0.776 newtons. Since it is positive, positive would be up. And that is the resultant I get for these three vectors using a scale diagram. Next, I'm going to do the same question, but now using a calculation. So, in a calculation, there's no need for measurements, which is why it's sometimes kind of preferable. So, drawing the three vectors once again. So I had F1, 100 newtons, that was 30 degrees that way. I had F2, which was 193.2 newtons, that was 75 degrees that way. And I now know what F3 was. It was 273.224. I am keeping this third decimal place here because I'm nowhere near my final answer yet. Okay, so this method 3 is using components, breaking it down into a vertical and a horizontal. So in doing components, colors are something that are useful here. That is something useful. So F1 I can break down into a vertical component. Let's call that F1 the Y part, and a horizontal component. Let's call that F2 the X component. Just redrawing that again. So this was F1. Don't care about the other vectors for now. Breaking it up into, there's going to be a horizontal part and a vertical part, means replacing this one vector by two separate vectors. Kind of the opposite of a resultant. So you could do it by taking that as being your Y component and that as your X component, which is perhaps the easiest way to do it because you already know what this angle is here. It's 30 degrees. Alternatively, you could break it up using that as your X component and that as your Y component, but then you wouldn't know what this angle is here. But if you look carefully, you can actually figure it out. Complementary angles add up to 90 degrees, so this is 60 degrees. but this is just an alternative way of doing it. I'm going to go using this simpler method and go ahead and work out my components. So, if I look at F1, the 100 newtons force, to get the vertical component, I'm looking at F1y. I know this vector here. So looking in this triangle, I have a hypotenuse. I want the adjacent side. The trig ratio that links them together is cos. So cos of theta, just to remind you, is adjacent over hypotenuse. From my triangle, that's cos 30 is adjacent, is F1y. The hypotenuse is 100. And so F1y will just be 100 cos 30, which gives me exactly 86,60 newtons. Now it is a component, so it does need a direction. Just based on my picture, I'm going to take that as being up. Right, next looking at how we do the horizontal component. So again, looking at this picture, the horizontal component here is opposite my angle. So the trig ratio that I'll use for this will be sine, because sine is opposite over hypotenuse. Just jumping directly into the numbers here, sine 30 will be the opposite side, which is f1x, divided by the hypotenuse. And this comes out to be exactly 50. Nice numbers. And the direction, take care with this in components, is left. Right, doing exactly the same thing now to F2. So F2 was 193.2 newtons. This is the angle that was given. So linked to this angle is where I'm going to draw my components, F2x and F2y. Okay, so if I use the adjacent side and the angle, that's a cos ratio. So doing things slightly shorter here, cos of 75 is the adjacent side, F2x, over the hypotenuse, which is 193.2 newtons. F2x comes out to be 50 newtons exactly. Well, 50,0003. If you want incredible accuracy, you can take that last decimal place, but here it's not going to make too significant of a difference. And this direction is now right. Great. Okay, the other trig ratio I'm going to use is the sine of 75. The separated side, I thought of it, or the opposite side as you know it, is F2y over the hypotenuse, 193.2. F2y comes out to be 186,617 newtons. And that direction from my picture, that's why pictures are important, is up. So those are your four components. Now we can work with the resultant. The whole point of working out components is it's much easier to calculate perpendicular components and add them than to add things at an angle, because, well, you can't mathematically. So first working with the horizontal part of the resultant. So how I write this is the resultant component, the resultant x component is going to be the x component of my first vector plus the x component of my second vector. So here's why notation is important, because now you need to find the right value. F1x was 50 newtons left, F2x was 50 newtons right. So you can see these vectors will kind of cancel out, but to write this mathematically, I can write it as positive 50 plus negative 50, where in this case I've taken left to be positive, because 50 newtons left I've substituted as positive 50, and that gives me 0 newtons. Although it's the same answer as just saying 50 minus 50, this is a much more physical, as in it shows the principles of adding vectors, as adding a negative as opposed to just minusing them. Anyway, that's just a technical point. Now looking at the resultant. for the resultant, I'm taking the y component of f1, the y component of f2, let's find those. I've got 86,6 up and 186,617 up as well. So they're both going up, so common sense tells you, let's take up as positive to make life simple. f1y, I'll substitute as a positive 86,6. Add positive 186,617. Then we punch buttons to get 273,217 newtons. That was positive, so it must be up. So this is the resultant of the two vectors I've worked out. Nice and simple, there is no horizontal. Now, just because you get tired does not mean you're done with the question. Whenever you think you've done, or at least done enough, always go back to what the problem was, and remember our saying, to read the full question. The full question in this case was to find the resultant of all three vectors. What I've done here is broken down the first vector into components, the second into components, and found the resultant of the first two vectors. So this answer here is actually f1 plus f2. Now before I go on and add the third vector, I just want to quickly compare that to what I got by scale diagram. So calculation gave me 273,2. In my parallelogram method, I got 268 on the first shot. In my triangle method, I got 274. So I wouldn't say they're both wrong. They're both inaccurate, meaning not exact, but you can see that the triangle method, for me at least, was slightly more accurate than a palm. But each time you do a scale diagram, your answer will be slightly different. Okay, so just want to put this with a sketch. So I have this resultant here, f1 plus going up. f1 plus f2 is 273,22. And then my f3 vector was, what is this? 273,224. So if I write this as the total resultant, it's the resultant that I got using vector 1 and 2 plus the resultant from vector 3. So this is 273,22 that was up, so I'm taking up as positive, and minus 273,224 newtons. So if you add these two things together, you will get minus 0,004 newtons. And if you round that off to 2 decimal places, as you're supposed to at the end, you get a grand resultant of 0 newtons, which is a significant number, because this is saying that that vector plus that vector plus that vector have the same effect as no vector. Now the word given to these three vectors that add up to 0 is, we call these forces in equilibrium. Equilibrium means balance. Basically, these two forces balance each other out. So the net force is 0. And in terms of what we describe as the effect of forces, if something has a net force of 0, that could mean one of two things. So going slightly beyond what the problem asked me to, if the net force is 0, that either means this thing is at rest or is going at constant speed. From our section on kinematics, if something is at rest, that means the velocity is 0 and the acceleration is 0. If something is at constant speed, that means velocity is, well, it could be any number, but acceleration is also 0. So what you can deduce from this is, if the net force is 0, acceleration is also 0. So we're getting to a kind of relationship, let's ignore that, where the net force and acceleration are related somehow. And that relationship is something we'll see in Newton's second law. So that was 30 minutes showing you how to add vectors using components by calculation, by a parallelogram method on the left and a triangle method. 30 minutes in showing you how to do it. try to do it yourself and time yourself on time management. Just before I end off, roughly as an estimation of marks, which is only useful in telling you how much time it should take you. For this first scale diagram, I would roughly, just making this up on the spot, say that maybe you get 2 marks for drawing this vector, 2 marks for that vector, and 2 marks for your resultant. And that's on a very generous day. So this, about 6 marks, should take you 6 minutes. And whichever method you choose should take you the same amount. When it comes to a calculation though, here, even though it's a very long calculation, the marks are kind of, I won't say stingy, but there for you to work efficiently through the problem. So in working out these components, probably get a mark for this component, mark for that one, mark there, and a mark there. For working out the resultant components, a mark there, and a mark there. So far, this is 7 marks. Now what did simplify this problem is that the resultant horizontal force was 0 newtons. If it wasn't 0 newtons, there would be an extra step in this calculation where you would have to use Pythagoras and then trig to work out its angle. But based on how the question was asked here, I would say this is about out of 7 marks. Now if the question was just given as such and you were free to choose any method you like, it wouldn't give you more marks to use a calculation method over a scale diagram. So this shows you how a scale diagram, I mean if you just look at it, actually is pretty simple. There's not a lot of maths involved, there's just drawing and accuracy compared to this whole page of algebra, but this gives you a more correct answer. However, you must be able to do both, because if a question specifies that you must calculate the answer, calculate means use numbers, or if it says determine, determine means to solve the problem either way that you would like to.